This video, I'm going to show you how to calculate how much of GPU RAM you need to either run or fine-tune a large language model. So without further delays, let's jump into the main topic of this video. We're going to start by learning what a weight is. So let's ask ChatGPT what exactly a weight is. What, what is weight when we are referring to large language model? Let's see what ChatGPT has to say. All right. So ChatGPT is saying that weight typically refers to the parameters or coefficients, right? So what exactly that statement means? It's simple, okay? So the weight is equal to parameters, but what exactly a weight is, right? So ChatGPT is saying that the model has learned during the training process. So this weight is something which large language model learns during the training process. Okay. So how exactly the weight is represented? Okay. So let's see what ChatGPT says here. Does it say anything here? How exactly it's represented? It doesn't say anything, right? So let us ask ChatGPT. Okay. How exactly weight is represented in the large language model? Okay, so if you see here, right, now it's saying that weights are represented as numerical values. So three key things. One, a weight is a parameter, right? And a weight is something which large language model learns during its training process, right? And each weight is represented as numerical values. Got it? Next, let's go to the next topic, bits, bytes, floating precision, and quantization. For that, I'm going to open up a whiteboard. Okay, so bits. What is a bit? A bit is either 1 or 0. Computer always stores the data in ones or zeros, right? Everything is stored in 1 or 0. Okay, so one more thing we need to learn or understand is what is a byte. A byte is 8 bits. So for example, like this 1100, 1100, 1, 2, 3, 4, 5, 6, 7, 8, or it could be 0, 0, 1, 0, 1, 0, 0, 1, 2, 3, 4, 5, 6, 7, I don't know, 1. Okay, so every 8 bits, binary bits, has some numerical value associated to it. So let's ask ChatGPT what is the value of this one. Okay, so convert the binary representation 1100 into numerical value. Okay, let's see what ChatGPT responds. So ChatGPT is doing some calculations, but in the end, the ChatGPT is giving a value, right? The actual value in terms of human readable values is 204. So 1100 is 204. So whenever you write 204 in text pad, notepad, no matter what, but whenever the application saves, the computer saves in zeros and ones like this. Okay. Okay, we're gonna park this information aside and we'll go to something else called floating precisions. Okay, so the full precision is called FP32, half precision is called FP16, and then there is something called int 8 precision and there is int 4. Okay, so FP32, if you see here, 32 refers to 32 bits, right? So now if you want to know how many bytes does this 32 has, all you need to do is just divide by 8, right? So if you divide 32 by 8 is 4 bytes. Okay, it's like 8 bits plus 8 bits, 8 bits, 8 bits. See, 8 plus 8 plus 8 plus 8 equal to 32, but each 8 bit is 1 byte, 1 plus 1 plus 1 plus 1, so it's going to be 4 bytes, right? So FP32 has 4 bytes, or I can say FP32 takes 4 bytes of your memory. Okay, so FP16 is half of 32. If 32 takes 4 bytes, it only takes 2 bytes, right? And 8 bits means it's only 1 byte, and 4 is just half a byte, 0.5 byte, or I can write like this, half a byte. Okay, so keep this information aside. We will see how this information is useful in our calculations. Okay, so think large language model like application, and the sole purpose of the application is to predict the text. Okay, what comes next. Okay, the sole purpose of the application is to predict. Okay, so let's say there is some rhyme. Okay, twinkle twinkle little, and you want large language model to predict what comes next, right? So let's say your large language model is trained on all the kids rhymes. Now the large language model can predict what comes next if you give a rhyme. As we already learned that during the training process there is something called weights, right? The large language model learns a weight, right? So what exactly that means is it gives a numerical value to each of the word. So let's say this twinkle, it gives a numerical value, I don't know, 2.756. So this twinkle is 2.756, little probably 2.95, and now you have to know what comes here. This is very simplistic explanation. Okay, it is much more complicated, uh, but just for the viewers, and I want this to be beginner friendly, so I'm just giving all these simplistic values. So every weight has a numerical value. So during the fine-tuning process, this large language model has given weights like this. Now you want to come up with the weight here. So large language model during inference, it does some calculations, a lot of calculations. We're not going to go into those, what calculations are those, but it does some calculations. And what it does is it comes up with a number. Okay, let's say 3.1. So it understands that after 2.95, 3.1 has to present. So now the 3.1 may refer to the star. You give some bunch of text, it predicts what comes next, and it does based on the weights. Now let's combine everything together. So now we understood that a weight is a numerical representation which a large language model learned during the training process, right? Okay, so let's say we have FP32, right? FP32 means it has 32 zeros and ones. Starts with 0 and it has 32 zeros and ones. 1 0 1 1. And FP16 has 16 zeros and 1. Let us ask ChatGPT something else. So let's ask ChatGPT what is the range of numbers for FP32. Let's see what it's going to say. Okay, it's giving some explanation, but we are only interested in the actual value, right? So now if you see here, it's giving the actual value as this much. Okay, if you see here, the range is, so it can have a range of numbers from this to this, and if you see, it's huge. 10 to the power of 38, it's huge. 10 to the power of 45 minus 45, it's huge. So let us ask ChatGPT what is the range of numbers for FP16, right? FP16. So let's see. All right, so if you see here, the range is 10 to the power of minus 5 to 10 to the power of 4. That's lot less than FP32. So what exactly I'm trying to say here is, if your large language model is on FP32, which means it has lot of weights, and lot of weights are distributed in this range. But when it comes to FP16, you see the range is very less when compared to 32. Let's say we are discussing with about the 7 billion parameter large language model, which means all those weights are distributed within this range. Okay, so now you can already see that there is a significant hit on the precisions, right? Then let's say now you have converted your model in int 8. So let's see what is the range for int 8. It's minus 128 to 127. So now when you put or when you convert your large language model from 32 to 8, which means all of the weights are within this range, minus 128 to 127. So let's say your base model is on FP32 and now you want to shrink the size, so you apply some quantization techniques. By the way, quantization is something where you are converting your base model to from one floating point, usually the higher one from 32, either to 16 or to 8 or 4. Okay, but what's happening here is whenever you do the quantization, the amount of GPU RAM you need to load that large language model decreases significantly, right? So if your base model is on 32, when you're converting to 16, it cuts by half because 32 takes 4 bytes and 16 takes only 2 bytes. But let's say you are converting the base model again from FP16 to 8, int 8, it again cuts by another half, right? So because int 8, it only takes 1 byte of memory. So let's say there is a 7 billion parameter model. Okay, so now we also understand that a parameter equal to weight, right? So now if there's a 7 billion parameter model, which means it has 7 billion weights, right? So if this base model is on FP32, right, we know that each weight is represented as a FP32 and FP32 takes 4 bytes, right? So if there are 7 billion parameters, then 7 billion parameters times 4 is how much of memory you need. So 7 times 4 is 28. On full precision, because it takes 4 bytes, so each weight needs 4 bytes and there are 7 billion weights. So when you multiply, it comes to 28 gigabytes. You can do quantize and you can do it on FP16, right? In that case, what happens is 7 billion times 2, you only need 14 gigabytes, half of it. Okay, you cut down the memory requirements now. So you can say I will do it on int 8. That would take only 7 billion times 1, you only need 7 gigabytes. BFP16. B stands for brain and it's floating point 16, right? So this is by Google. Let me show you an article where it actually explains about this BF16. Okay, so this is an Hugging Face. If you go here, there are different floating points, but if you see here, right, float 16, the regular float 16, the exponent part is represented only in 5 bits, but the exponent part of BF16 is in 8 bits. Same thing as float 32 is again exponent part is 8 bits. There is a change in mantissa. If you see 8 bits for BF16 and 24 bits for float 32, but the main thing is the exponent part, they managed to keep it same. Okay, so whenever you're trying to quantize, do not try to quantize from FP32 to FP16, normal FP16. Try to quantize on BF FP16 so that your performance or the response or quality of the responses of the large language models is not degraded as much. Next, so now we understood that by quantizing you can decrease the amount of GPU RAM needed, right? All right, so let's say you have a base model of FP32, you quantize to let's say int 8, right? So now you might be thinking that let's say it's a 7 billion parameter, int 8 times 1, 7 gigabytes. Is that all we need? No, there is something else you need to know. Okay, so let me show you something. Let me run something on my local. Okay, so if you see here, I will be running Mistral 7B large language model. Okay, but the key point I want you to see is, okay, this is a quantized model which I'm running in my local, but the key point I want you to focus on is this one. Context length is 250. Okay, so let me try to run this, or let me try to load. So everything's loaded, and if I see here, I want you to see that the amount of VRAM for this context length of 250, the amount of VRAM we need is only 31.25 MB. Okay, this is how much GPU RAM is needed. Plus, it also adds some buffer, which is 41.27 MB. Okay, so what I'm trying to say is, when the context length is small, so whatever the amount you need, or whatever the amount you got by multiplying your 7 billion parameters with either times 4 or times 2, that's all you need to know. But let's say the context length is, I don't know, let's say 12,000. Now let's see. Now let's see how the numbers are. Come down, come down. Dun, dun, dun. Okay, so now the context length is 12,000, but if you see, because the context length is 12,000, I need another 1.5 GB of VRAM, plus I need another 784 MB of VRAM. So if you add this together, it's going to be more than 2 gigabytes or something, right? So the point is, let me show you. The point is, it's not just this 7 GB, it depends on what is the context. And you might be wondering, all right, I understood, but what exactly is the context? Okay, context is whatever the input you are giving to the large language model. Okay, so let's say if it's a 200 context length, it's 200 tokens. You might able to fit, let's say one word is one token, you will be able to only fit 200 words as a prompt. Okay, but now let's say you want a huge prompt. Okay, huge prompt, and in the prompt you also want to provide some information to the large language model, then 200 tokens is not enough. Maybe 4,000 tokens, maybe 12,000 tokens, maybe 32,000 tokens. Okay, so based on how many or what is the context length, your GPU requirements vary. Okay, so there is one more thing we want to understand is activations, right? So what is activations? Okay, so let's ask ChatGPT what is an activation when we are referring to inference. Okay, what is activation when we are referring to inference of large language model? Okay. Before ChatGPT gives the response, I actually forgot to explain one thing that is called inference itself. So what is an inference? An inference is something you are running a large language model, you give some input, and you're expecting a output, or a response. That's it. That's our inference. Okay, so this activation plays a key part in the large language model responses. Okay, so let's see what it is saying. Okay, activation typically refers to the output of a neuron, and then it's also saying that during inference the model takes an input and process it through its layers to generate an output. Okay, so now there is a new word here, layers. Let me show you the layers as well. If you go here, I just loaded this my large language model, right? So if you see here, I'm actually loading the layers. Okay, if you see, all these are layers. There's so many layers which I'm actually loading onto my GPU. So what ChatGPT is saying is, model takes an input, it processes through its layers and generate an output. It's a very simpler way, right? But there is something called activation function. Okay, let me explain in the whiteboard. So let's say how the large language model is, it has nodes. Okay, it has so many nodes, and there is something called activation function. Okay, so a function in any programming world is something which takes an input and gives out an output, right? It or it just does something. It doesn't always have to give an output. It can also do something but does not give an output. So let's say you give a input, right, to the LLM. Let's say the context length is 200, which means you pass 200 tokens. Okay, so this 200 tokens goes here, goes here, goes here, goes here, goes here, to all the neurons. Okay, so now what's happening here is there is some calculation going on. There's a lot of calculations going on. Okay, so that's why, see, the more the tokens, the more the calculations needed, which means more resources you need to allocate for your large language model to do those calculations. So but for now, let's say you are only passing 200 tokens, so it is calculating. So this node spits out something, right? Some value 3.2, some value 3.6, 4.5, I don't know, 5.5, 7.8, or 7.9. So what happens here is all these values goes through the activation process. So what exactly large language model is doing is it's asking this activation function that should I activate this neuron or this neuron or this one or this one or this one or this one, and activation function based on the values, it actually activates one neuron. Maybe it want to activate based on the context and everything, maybe it want to activate 5.5 neuron. So whatever's in here, output comes as 5.5. So this is the most basic explanation. There is a lot going on, but to put it in simplest terms, this is what happening. So that's all for the inference. The last topic or concept which we need to learn is fine tuning. Okay, first we need to understand what exactly a fine tuning is, right? So whenever you see a large language model like Llama 2, right, it's a base model. It's a pre-trained model. They train the model with lots of data. So that's a pre-training. Okay, so that pre-trained or base model, even though it's a large language model, it has no purpose. It has no specific purpose. You give some input to it, it gives some random output because it doesn't understand the context. It doesn't understand what exactly you are saying. Yes, it has lots of weights in it. It has lot of information. It just don't know how to use that information. So if you want to use a large language model for your application, so you need to fine tune that large language model. So how do we fine tune a large language model? That's a whole different topic, but what are the basic concepts you need to know to understand that how much GPU RAM you need to do a fine tuning. To do the fine tuning, the base thing is you need a model. So let's say the base model is 7 billion parameter. So you need to load this model. If you're loading on FP32, so that's going to be 7 times 4, that's going to be 28 GB. So you need at least 28 GB just to load the model. Okay, but let's say 28 GB is out of your scope. So what you can do is you can either quantize to FP16, int 8, or int 4, right? This is very aggressive, but int 4 quantization is not something we use. There's another quantization called NF4. Okay, it's called normal float represented in 4 bits. So for this video, we only gonna, whenever I say 4, I'm actually referring to NF4. Let's say 7 billion parameter. Now you are doing on NF4, right? That means 7 times, because this is precision is 4, you only need half of a byte for each parameter, and there are 7 billion parameters, so it's going to be 3.5 GB. So you can load a model if you have 3.5 GB. Okay, but that's just loading. There's a lot more to the fine tuning. If it's just an inference, yes, you need a 3.5 GB plus whatever the context length needs, right? But this is not inference, this is fine tuning. Let us go through the slide and I'll show you something. There is something called gradients, there is something called optimizer, and there is something called activations. Okay, so let's say you load a model, it takes some RAM, right? X RAM. So you need the same amount of X RAM for the gradients. Okay, then you need some RAM for optimizers. Okay, so the most popular optimizer is Adam. Okay, so but the optimizer, what we need to understand is it's not just X, because there are 7 billion parameters. You might say that, oh, the optimizer, it only takes whatever it takes for to load the model. No, it takes twice the amount of X. What's next? Then activations. It needs X. Let's say you are loading a base model on int4, right? So we just calculated by 2, that's going to be 3.5 GB. The gradients, you always have to load either on FP32 or FP16. If you wanna, if you have on memory constraints, just go ahead and do it on the FP16. Okay, so now there are 7 parameters times how much? FP16 takes 2, right? 2 bytes. FP16, it takes 2 bytes. So there are 7 billion parameters. Each parameter or each weight needs 2 bytes. So 7 billion parameters needs 14 GB. That's a lot. So that's where a new technique called PEFT comes into the picture. Okay, it's called parameter efficient fine tuning. So what they are saying is, according to this paper, you can load the model. Okay, you can load the complete model, but you don't have to train all the parameters of the model. Okay, you don't have to. You might have to only train a few or subset of parameters. Let's say out of 7 billion parameters, you only have to train 500 million, right? That is half a billion meters. So what PEFT says is, instead of loading all the parameters, all you have to do is just load the necessary parameters and fine tune those parameters. So let's say you are only trying to fine tune 500 millions, that is 0.5 billion. Okay, and these 0.5 billion or half a billion parameters have to be loaded on FP16, which is equal to 1 GB. But this is the parameters, PEFT parameters, which you are loading. So you have to do a gradients on this, right? So it's going to be another FP16. So you need another 1 GB. Got it? So right now, instead of 3.5 GB plus 7 GB, in the before slide, whatever we calculated, that gradients need 7 GB. Now we are down to 3.5 GB plus 1 GB plus 1 GB, that is equal to 5.5 GB, right? Let's see how it's going to affect optimizer and activations. Okay, so I'm going to do again. The base model is 7 times 0.5 equal to 3.5, and now the PEFT model which you are loading, the only the trainable parameters, it's a 0.5 billion times 2 is equal to 1 GB, and also the gradients, now because you only are training these, 0.5 times 2 is equal to 1 GB, right? So now what's next? Go to our slide to understand optimizer states, right? So now optimizer states, like I said, Adam is in either 32-bit or 16-bit or 8-bit. Okay, so let's say you want to use 32-bit, right? So 2 times, because I just explained that optimizer, it needs twice the amount of parameters, right? But how many parameters we are using to train? Only 0.5. So 2 times 0.5 times 32-bit means 4, right? 2 times 0.5 is 1, 1 times 4 is 4 GB, okay? But let's say you want to do it in 16-bit. What happens now? 2 times 0.5 times 2, right? 2 times 0.5 is 1, 1 times 2 is 2. Okay, and then it's going to be the same thing, 2 times 0.5 times 1, that is 2 times 0.5 is 1. Okay, so now because of PEFT, what happens is, because you're using PEFT, you're only loading few parameters to train. Even the atom, whatever the memory requirements for the atom is decreased. Okay, so if you use, let's say, 8-bit with this one and only half a billion parameters, you end up with having only 3.5, 1, 1, 1, right? 3.5, 4.5, 5.5, 6.5. Okay, so that's about the atom. Okay, again, there is something else we need to understand, and that is activations. Just like there is an activation in inference, there is also activations during the fine tuning. So just say that whatever a base model takes, activation takes. Okay, if the base model is x, it takes x. Okay, so now it takes 3.5. Okay, so now if you calculate everything, 3.5 plus 3.5 is what? 7, 8, 9. Then based on the atom, either you can get 13, 11 or 10 GB. All right, okay. So there is one more important topic you need to understand, or a concept you need to understand, and that is batch. Okay, during a training you usually do batches of 32, 64 or 8 or 4. Let us ask ChatGPT. Okay, what is the main advantage of doing, or advantages of batch in fine-tuning large language model? Let's see. Okay, yeah, so this is what I'm trying to explain. So stability. Okay, so the batching actually helps your training is stable and smoother. Okay, so the more the batching is, your training or your loss curve would be smooth. Okay, there are other advantages, but what I'm saying is, if you don't do batching, your training would not be smooth. Okay, your output or your large language model does not perform as good as you expect. But to do the batching, you need a lot of GPU RAM, right? Okay, you need a lot of GPU RAM. So let's say you want to do batching 8. So if you do 8 batch, you might not have enough GPU RAM, but there is a way where you can actually do a batching, use a batch, but still not use RAM, a lot of RAM, and that is called gradient accumulation. Okay, so what you can say is, you can put batch is equal to 1 and accumulation is equal to 4, which means effectively you are running the fine tuning on 4 batch. Okay, it takes time. That's the trade-off. Okay, if you're doing gradient accumulation, it is slower. Okay, but that's a trade-off. If you don't have GPU RAM, then the next best thing where you can achieve the same kind of batching results is using the gradient accumulation. All right, so what did we learn so far? We learned about weights, we learned quantization, we learned all the floating points, we learned inference, and I also explained what is an activation, what is a weights when we are considering inference, and what exactly we learned in fine tuning is we need a base model, load the base model in whatever the precision you want, and just load the trainable parameters using PEFT, and there will be a GPU memory allocated for these trainable parameters for the gradients, then for the optimizer, then for the activations. All right, and that's it for this video. Thanks.